right, gang. Today we're going to talk about, begin with the M. Momentum. Hey, momentum. Hey, which has the greater mass? A roller skate or a Mack truck? Will I ever check your neighbor on that? How many say, well, gee, I might be wrong. It must be a trick, maybe a roller skate. Yeah, which has more mass, a roller skate or a Mack truck? Come on. A Mack truck. By far, right? Hands down. Which has more mass? A Mack truck moving or a roller skate moving? Same speed. How many say, now they get the same mass? Show of hands. Good. How about this? Which has more oomph? A Mack truck moving or a roller skate moving? Check your neighbor. More oomph. The Mack truck got something more than the roller skate. And what is it, gang? What we're going to talk about today, momentum. It's got more momentum, more oomph, okay? Oomph. And let's define momentum. Momentum is not just mass, not just inertia, but inertia in motion. So we define momentum to be the inertia of something, its mass, multiplied by how fast it's moving, its velocity. So momentum is mv. So when I ask you the question, which has more momentum, a roller skate or a Mack truck moving at the same speed, you would say, well, if the speeds are the same, the momentum will be the same. Any fool knows that, right? But fools aside, what would you guys say? The Mack truck. The Mack truck, because it's got more mass. Can you think of a case where the moving roller skate might have a greater momentum than a moving Mack truck? You take the mass of the Mack truck, humongous, multiply it by its speed, you get a number. Now take the mass of the roller skate, tiny, tiny, multiply by its speed, you'll get some number. And you could make that number bigger, couldn't you, if v was enormous for the roller skate. Isn't that true? So momentum really involves not only inertia, but how fast the inertia is moving. Inertia in motion. You have that kind of idea? And that's what we're going to talk about today. And today's stuff is all common sense, and it's an outgrowth of Newton's laws. If that roller skate is running down the hill, and that Mack truck is running down the hill, and you've got to stop them, you've got to step out in front, put your hand there, and force them to a stop. There's going to be a difference, isn't there? It's going to be a lot harder to stop the Mack truck. Why? Because you're going to have to decelerate it. You're going to have to decelerate it. And it takes not only a lot of force, but I mean, how much force is it going to take to decelerate the Mack truck compared to the roller skate? A lot or a little? A lot. Why? Because the Mack truck has a lot of mass. So, honey, to decelerate that, it's going to take a lot of force. Remember we talked about acceleration? Acceleration, what? The amount of force applied upon a particular mass will yield a particular acceleration. Are we getting now so we can read equations? Okay? That's Newton's second law. And then this is how you get acceleration. And what is acceleration by definition? If someone asked you, okay, that's how you get it by pushing on a mass, but what is acceleration? You would say, check the neighbor, what is acceleration anyway? Change. It's a change. A change in what? A change in velocity? Over time. Okay? Here's how you get acceleration, and here's what it is. So you know what I can say? This must be equal to this. And now I can say force multiplied by time. Watch this. Can you guys do a little algebra? Force multiplied by time must be equal to mass multiplied by change in velocity. I've just cross-multiplied. This is going to allow me to look at things with a little more perception than otherwise. See where I have the m and the v? I can put them together. What do I call this quantity here? Check the neighbor. See if the neighbor knows what the quantity mass times speed equals. A. Begin with an M. How many sitting next to someone who has no idea? Okay. Change seats, yeah? Okay. See where I have this change in, gang? Change in. I'm getting tired of writing change in. Ain't going to write change in anymore. I'm going to use a Greek symbol for change in. What's the symbol, gang? Delta. That's right. So I'm going to write that from now on as F multiplied by T equals change in. Get it? Delta mv. This is what we're going to talk about today. So this delta mv, that's delta momentum. We have a name for force times time. What's the name of the force of an object multiplied by the duration of time in which that force acts? We have a name for that. It's not so common a name as this one, but see if you're sitting next to someone who knows what is the name of force multiplied by the time during which that force acts. Go. Talk it up. What is it, gang? What's the name of this? What? Impulse. Impulse. All right. Impulse. Okay. So we write. Impulse equals change in momentum. That's what we're going to talk about today. You want to change the momentum of something? Then you have to apply an impulse. What's an impulse? That's hitting it over some time interval. Down here I have a, see that golf ball on the tee? See this golf club right here? What's the momentum of the golf ball right now? 0. Watch this. Now the golf ball has momentum. How did it get it? How did it change from 0 to something? How did it? Because I hit the darn thing. That's how come it did, right? Okay. And if I want to change the momentum a lot, how do I hit it? A little or a lot? Hit it a lot. And I want to change the momentum of that golf ball humongously. I hit that thing as hard as I can. And all we're saying here is, let's see if we can read the music. If you want to get the momentum to change a lot, then apply the biggest force you can. Hit it as hard as you can. What's the T for? That's why you follow through. When you hit it, you don't just and stop. You hit, you make that force last as long as possible. And if you can like double the time during which that force acts, what will you do to the momentum? Double it. Let's suppose you can hit it so that follow through makes the force, pretend, it makes the force last 3 times as long. 3 times as long. So 3/10 of a second instead of 1/10 of a second. How much will the momentum change? 3 times. How much does the mass change? Not at all. So what changes 3 times? How fast the ball goes. How fast the ball goes tell you how far the ball goes. Isn't that true? So you follow through to get the most momentum possible. Let's suppose I have a slingshot. I got the rubber band here. See that? And I take the rock and I pull it way back. Okay? The further back I pull it, boom, the more change in momentum I will get for 2 reasons. See if your neighbor knows what the 2 reasons are for pulling the elastic band way, way back. You get even more speed when you let go. Now everybody knows that. Every child knows that. You pull it back like hit, plop. Hit, hit, plop. Now, bam! Everybody knows that. You guys do too. Now what are 2 reasons pulling it all the way back gives you more change in momentum? Check your neighbor. Okay, what's the reasons, gang? You're going to increase the force. When you stretch that elastic way, way back, there's a bigger force acting in that little rock that's going to be flying out, huh? A bigger force. What else? That's right, it's going to have a longer distance. It's going to take a longer time to spend, right? Okay, so the longer the time that acts, the greater the force that acts, honey, that slingshot going to fire faster. I mean, further. Yeah, yeah? It makes sense, huh? Hey, how about a cannon? How about you got a couple of cannons? You got one short, stubby cannon, and you got the same darn cannon, except the barrel's longer. Now you fire the cannonball. Same amount of powder. Which cannonball goes further? The long barrel, the short barrel, or same? How about the people say, well, you got the same kind of powder, you get the same cannon, one a bit longer, so what? Same cannon, same oomph. Hey, they both go the same. What do you guys say? Someone say, no, the long barrel, the cannonball will go further because there's more force acting on it. True or false? The answer begins with an F. It's because there's more what? There's more time. The cannonball is in the barrel for a longer time, being push, 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 push. It's going to go a lot further if the cannon is a lot longer. Can you see that? Okay. And all that stuff makes sense here, doesn't it? Huh? So we find out this physics we're talking about is really the physics of common sense. How about you? You're riding in a car, and the brakes have failed, and you got to stop the car. Which is going to require the greater force? Let's suppose you got your multiple choice. Either you drive into a haystack, or you can drive into a cement wall. In both cases, you're going to come to a halt. In both cases, you're going to, if you're going at a certain speed and you come to a halt, in both cases, you'll have the same change in momentum. True or false? You're driving 60 kilometers per hour, boom. After impact, you're going 0 kilometers per hour. You've gone to 60 to 0 in both cases. So in both cases, you have the same change in momentum? Yes. Do you have the same impulse to stop you? Yes. Do you have the same force to stop you? I'm saying, wait a minute, you said force, you said impulse. I don't know which is which. See, gang? Here's the critical thinking of the course. See? The impulse is the force multiplied by the time. But the force is not the impulse. It's part of it. So what happened? What are you going to hit, the haystack or the cement wall? How many say, well, either one's both the same. Same impulse. Yeah, same. You're not interested in the impulse. You're interested in the force. And what's going to be the bigger force? It's like this. You're going to change your momentum. Now you got a multiple choice. If you hit the cement wall, these two numbers will multiply together to give you the same number as this. But if you hit the haystack, take a long time to slow down. Now, which do you want? Okay. Yeah. You're at the top of a cliff, and you got to jump because the fire is coming closer and closer. And you look down and you see a circus net over here, and over here you see a concrete parking lot. Yeah, well, I don't know, either one. I don't know. Come on, which would you jump in? Now, if you didn't have any physics, you'd probably jump into either one, right? Come on, no, come on. No. Everybody knows you jump in the net. Everybody knows that. Okay? And everybody knows that if you jump on the net, the force that acts on you ain't going to be so much. And everybody knows that if you jump onto the concrete parking lot, honey, that force is going to be humongous. Splat. That's the end. That's it, right? An enormous force. And some people know why. And those people is who? Us types. Okay, we know in such thing, right? Okay. Here's another thing, too. Let's suppose we went down to the football stadium and all the guys are practicing there. And we take someone who looks like they're really in shape, 220 pound or something like that, and we bring him up and we bring him into the gymnasium. We got the boxing ring there. And we put some gloves on. This dude is really tough. He's not so much into fighting, doesn't know the savvy, you know, but he's a strong guy. And then we invite the heavyweight champion of the world to come to the university to give a little demonstration. And we put the gloves on both. And this is just a sample athlete, okay, football type. And we say to the champ of the world, champ, this guy might not look like much, but I'm telling you, you better be serious. Take him out as fast as you can. So the champ means business. Now you ring the bell. Bing! They both come out. What's likely to happen? There's a very good chance our victim might end up with a tag on his toe that night and be stretched out on a slab. Because the heavyweight champion of the world comes, boom, and hits that guy. Good chance of killing the guy. Killing. Dead. HC. But, take that same guy and let him work out for a couple of weeks. Let him just move around, learn how to move, huh? And get a little ring savvy. And then have the same scenario happen again. Ring the bell, They come out, whoop, boom, hit, boom, he's down. But you know what? He gets back up. And the second case, he gets back up, and the first case likely doesn't get up at all. What's the difference, gang? What's the difference? Here's what happens in the first case. The guy comes out. Ding. Okay, this is the football hero. Comes out. Boom. That's it. That's all over. The second case, he comes out, sees the punch, pulls back a little bit. Even a little bit. Rides with a punch. When he rides with a punch, he'll go down maybe, but he's not going to be smoshed. Now, why does riding with the punch make a difference? I used to be into this stuff. When I was 17-year-old scout owner, I was a silver medalist in New England States. And I was into this as a teenager. I was really into that stuff. And I thought I knew the reason. I didn't know any physics then. But I knew why it was when you ride with a punch, you don't get hurt. And if you're coming in, you really get hurt. And I had it figured out. And this was my figuring. When that punch comes in, if you ride with it, come back like this, both are going in the same direction. And the speed of impact is going to be reduced. See? Because if you come in and you stop, boom, you get the whole speed. But if you come like this and you move back, it hits with less speed. Can you see that? See? And if you're coming in like this, boom, even more speed. And so I knew why. And what I knew turned out to be wrong. Because one day I was looking in these old ring magazines, and I saw an astounding fact that changed my whole theory. It demolished it. And it was a fact that said this, that a fellow by the name of Joe Louis, who was a heavyweight champ many years ago, they timed his right cross. They timed it. And they timed it to be 90 miles per hour. That's how fast it's coming in. And right away I says, wait a minute, honey, wait a minute. If this punch coming in 90 miles an hour and you stay there, boom, you're out. But it's coming in 90 miles an hour and you move back. Now let me ask you guys a question. How fast do I move back? How many miles per hour? 2 at most, right? 2. So if I come back, what's the velocity of the punch? 88. And what if I stay there? 90. 88, 90 is same. So you know what? That can't be the explanation. It doesn't have to do with relative speed. It has to do with something else. Check your neighbor and see if your neighbor knows what it is. Hint, hint, hint. What's it have to do with, gang? It has to do with the time. See, when you pull back, it takes a longer time for that momentum to spend. Let's look at the equation. Okay? We're saying that this is true. This is true, huh? Impulse equals change in momentum. Now let's look at this equation with respect to boxers and one hitting the other, okay? Let's suppose this is the force of the punch. Boom, huh? It's coming in, okay? This is the time of impact of the punch, right? What's this change in momentum? What is that? What's that M? If this is the force of the punch, this is the mass coming in. In a barroom brawl, this would be the mass of a guy's arm multiplied by the speed. See, my arm got momentum. It hits, boom, the momentum stops. The momentum changes. The momentum changes because it's an impulse acting. That impulse, that's the impact, huh? Now that impulse is going to be force multiplied by time equals a change in the mass of the arm times the speed. But that's a barroom brawl. The heavyweight champion of the world, you wouldn't put in M for the mass of his arm. Because the heavyweight champion of the world doesn't punch like that. Doesn't punch with his arms. The heavyweight champion of the world punches from about the ankles up. Oh, okay? The whole mass of the body is in there. From here up. And you take the mass of the whole person, then times the speed. Honey, that's a humongous momentum. And that momentum's coming at you. Now you got to stop it. And someone says to you, hey, well, you might as well get it over quick. Just stand there. Good idea or bad idea? So what do? You come back. You roll back and you make the time of impact, the time during which that momentum spends itself, you make that time as long as possible. And when you make the time long, then what happens to the force of impact? Short. You kind of see that? And what happens? You come in. Boom! It happens so quickly. So quickly. And very, very quickly, the force of impact is huge, and that's knockout time. Here's something I never could understand at that time, and that's this. You're going to get ready for your tournament coming up next Friday. 3 3-minute rounds. So for 3 minutes, you go on, boom, and 3 minutes again, and 3 minutes, that's it, the fight's over. Now, you go in the gym and prepare for this. You got to be in shape. So in the gym, what you do is you got the great big bag there, and you bam, 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 bam. You hitting that bag all day long, bam, bam. And you hours on that bag, and you feel good. You feel really good. You're tired, you get energy, but bam, you're hitting that bag, and you're saying, man, I hit this bag all day long, tirelessly. Okay, I'm in shape. And all I got to do is 9 minutes Friday night? Whew, no problem. And Friday night come. And at the end of the first 3 minutes, you go back to your corner and, you are tired. And you can't understand why. Because in the gym, you can hit the bag all day long. And in the first 3 minutes, boom, what's going on? At the time, I thought it was an audience thing, that you're more tense because all these people are looking at you. And that was my feeling. And my thing was, well, pretend they're not there and just do the best you can, okay? Psych yourself out. And later on, when I get into physics, I say, hey, son of a gun, I know what's going on. Do you guys see what's going on? When you're in the gym, you hit the bag, boom! You put a lot of momentum, crunch! That momentum stops. What stops it? The bag. The bag provides the impulse to stop the momentum of the punch. Now, opening night comes, a guy comes out, you throw it, whoom, he's down here. Whoom, he's down here. Whoom, he's down here. You miss. And every time you miss, you, boom. Who supplies the momentum to stop that punch? Myself. I throw another whoom. Who supplies the who, huh? It's not the impulse, I should say. Who supplies the impulse? Next chapter, we'll learn the energy. Where's the energy come from to stop these punches that are thrown? That's why you see good fighters. Good fighters won't throw so many. When they throw, they hit. If you're going to go 12, 15 rounds, you gotta, when you throw, you hit. You miss, 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 miss. You're not going to last. You're going to wear yourself right down. So the laws of physics, very important in sports. You're playing sandlot ball. You're walking across the ball field. These kids are throwing the ball back and forth, huh? You got no glove. Hey, kid, throw me one. Throw me one. Kid says, mister, you ain't got a glove. Got no glove, honey. Throw me one anyway. Hey, I'm in shape. Kid takes the hard ball. Now you catch the ball. How do you catch the ball? Man, that ball coming. Don't you put your hand way out here? And then you throw it back, right? Kid says, didn't it hurt your hand, kid? I mean, mister? No, I'm in shape. It hurt your hand kind of, didn't it, right? And the kid throws another ball. Don't you put your hand way out here? Why do you put your hand out here when you catch it? Why do you do that? Check your neighbor. You hold your hand out there so that when you catch the ball, what are you making bigger, gang? You're making the time during which the momentum of that ball cuts down to zero as long as possible. So you grab way out here and ching, 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 a lot of time, a little force. Ain't that right? And so the kid says, gee, how'd you do that? Say, my hand, I'm in shape, kid. Kid says, you got a strong hand, huh? Put your hand up against the board, man. Now we, what happened? You catch the ball now? Huh? Oh, okay. Then it'll be a short time. Short time, large forces. Let's suppose you want to get the largest force possible in stopping the momentum of something. How would you like to see a karate demonstration right now? I'm up to my white belt. All right. See this 4x4 oak? Can you see it? See it setting on these two little things right here? Can you guys see it? See that? Taking this piece of cloth and putting it around my hand, protect it a little bit. See that? Okay? How many people don't see it? We all see it. We're imaginative types, aren't we? Okay? Now watch this. I'm going to hit it, and I'm going to break that 4x4 oak. Okay, watch this. You see that? Boom. Done. Done. Look at it. Splat. Now, how was I able to break that? Because I changed the momentum of my hand in a short time or a long time? So short, you hardly saw it. Isn't that true? How about I do it like this, gang? Yeah. No way. No way. Man, boom, boom, done. And furthermore, if I do it in such a way, I don't pull my hand back. But if I do it in such a way that my hand bounces off there, whoo, honey, that is going to break. That is going to break. Because bouncing gives a lot more impulse than just hitting. You're walking along the street. There's a plant pot up above. The plant pot comes down and hits you on the head. Boom! It sticks to your head. You're in trouble. But the plant pot comes down and ba-boom! Bounces off your head. Honey, you are really in trouble. Because the bouncing gives more impulse. A lot of people have trouble understanding that. Let's see if we can understand it with this idea. Let's suppose you stand on a skateboard right here. You're on the skateboard. And on the skateboard, someone throws you a ball. Okay, the ball's coming. The ball has momentum. You catch the ball. Boom. Any impulse on you? Yes. And that impulse does what? Pushes you along, right? Okay. Let's repeat the experiment. This time, you stand on the skateboard, and you throw the ball. You give it the same momentum that you stopped it coming in, that it had when you came in and you stopped it. You gonna hear what I'm saying? When you throw the ball out like that, do you supply an impulse on the ball? Can you supply an impulse on the ball without the ball supplying an equal and opposite impulse on you? Before we said force. We can say impulse, because force times time, force times time. So when you throw the ball, what are you going to do? You're going to recoil. Do you see that? Do you see that if you throw the ball just as fast as you caught it, you'll recoil the same? Here's why. If you change the momentum of the ball the same amount each time, then you'll have on you the same impulse each time. Do you see that? Does this stuff mean anything to you? Some people look at F, a T, what's that, a Greek letter D, a M, a V, a equal sign, I don't know what I mean. Can you guys see that everything I'm talking about ties into this rule? Okay? Now here's the thing. Let's suppose you're on a skateboard and you catch the ball, and then you throw it back again. More impulse on you, or the same as if you just caught it? Check your neighbor. Can you see if you catch the ball and throw it back out again, that there'll be more impulse on you than if you only catch it, or you only throwing it? Or that when something bounces off you, it's in effect the same as catching it and throwing it, and a bouncing collision is going to give more oomph than just a sticky collision? You know who made a fortune on this? Back in the 1849, in the gold rush time in California. A lot of people made a lot of money. But one of the people to make the most amount of money was a fellow by the name of Lester Pelton. And what Lester Pelton did was he redesigned water wheels and had the good sense to patent his design. Water wheels at that time had these blades. And, didn't have electricity and power like we have today. So they would have a water wheel to turn the wheels at the gold mills, huh? And the water would come down, hit these paddles, kind of come to a stop and kind of go along with it. What Lester Pelton did was this. He redesigned the paddles. He made the paddles like that. So the water would come down, make a U-turn, and bounce back out again. And he made the paddles in such a way to make the water bounce. And when the water bounced off the paddle wheel, more oomph. And he made more money on this than most of the gold miners did on their claims. Simply using the laws of physics. You'll apply more impulse to that spinning wheel by bouncing the water than just simply catching it or stopping it. Ain't that neat? Any questions to this time? Okay. Here we have a little device called an air cart. And right now there's a lot of friction with these things. See, they kind of slow down very quickly. A body at rest doesn't remain at rest very long. A body in motion doesn't remain in motion because I've got an opposing force. And the force of friction, of course, is slowing these things down. What I'm going to do, though, is this is like a vacuum cleaner in reverse. I'm going to throw on the switch, and it's going to blow air jets. Air's going to cut them. You can't see that, but there's a whole lot of little holes there. And air is going to blow out. And these things are going to ride on a cushion of air. And it's pretty nearly friction-free. Let me show you what I mean. riding almost friction-free. Now let's see what happens here. Watch this. How come it moved? Let's try it again. And how come this stopped? This is common sense. But let's look at it with some care, and we might see more than we would see otherwise. Here's A coming in, and it hits B. When it hits B, what did we see? We saw this one stop and this one continue. And I asked, why did this one start to move? And you would say it started to move because it was belted, right? This one came in, A came in, bam, and belted it, and that's why it moved. When I say belted, more specifically, what happened? There was an impulse on this. Right now, its momentum is 0. This came in and hit it, and an impulse was applied to this. Let's look at only object B, only this one. And we'll focus all our attention on that. I'm going to put a dotted line around only object B. And I can answer the question why object B started to move. Because, bam, there was a force of impact of A on B. And that made B move. And so you guys saw B takes off. So it's easy to see why B started moving. Okay? An impulse acted on it. Its momentum changed. But did you notice also that the momentum of this changed? Let me show you again. Why did this one, why did object A slow down to a dead stop? What slowed this down? To say it slowed down is to say there was a change in momentum. True or false? True. And if there's a change in momentum, there has to be, true or false, an impulse. True. And did you see an impulse act on this? Yes. Yes, you did. Because if we look at this again. Okay, they hit. If we're only interested in A, we let object A be our system. Is there any force, any impulse acting on A when they collide? Yes. And what's the force that acts on A? B's hitting it. All right? All right? So see that arrow? Wham! So that's what stops A. Let's suppose we focus on both together. Momentum. Momentum. How big was the momentum of this compared to the momentum of this after collision? Did you see that? If we look at both, if we let our system, our concern be both, this acts on this, this acts on this, how much force is acting on our system? None. See? If our system is only B, then there's a force poking in there. There's a force acting on it, which provides an impulse, and boom, away it goes, B, huh? And over here, if we let our system be A, we can see there's a force from the outside that acts on it. The force of B pokes in and stops it. Now let's concern our system to be both together. Then this acts on this, this acts on this. The action and reaction are within the system. There's nothing poking from the outside. Let me ask you a question. For this being my system, what's the net force acting on it? 0. What's the net impulse acting on it? Not so many people said the same thing. You guys see the net force acting on a system is 0. What's the net impulse then? This is net force multiplied by the time. It's still going to be 0. So what's the change in my momentum if there's a 0 impulse? 0. And the momentum of my system doesn't change. This one stops and this one continues. This one continues with the same momentum this one had. Let's suppose the beginning one, let's suppose this had 5 units of momentum. Boom. Comes to a halt. How much momentum does this move with? So what's the momentum before and after the collision? 5 5s, no change. Which turns out to be a very, very neat idea. And the idea is this. If there's no net force acting on your system, and when you say system, depends, what do you mean by a system, gang? See, I've got 3 systems here. But if I have a system such that the net force is 0, then the impulse is 0. That means the change in momentum is 0. Careful, it doesn't mean the momentum is 0. It means the change is 0. So whatever momentum you have before something interesting happens, you'll have the same momentum after. That's a very powerful idea, and it underlies a lot of physics. Take a spinning system. It's got momentum. Let the system blow up, do whatever you want. I don't care what it does. Check that momentum afterwards, and guess what you got? The same momentum. When you study astronomy, that will be a pillar from which you will build many other ideas. That the momentum that a system has, if you don't mess with it from the outside, whatever momentum it has, it's going to stay. It can't change unless there's an outside force. Outside force means outside impulse. You know that you're sitting in your car, and the car battery is dead, and you got to get out and push the car, but it's raining. So you say, well, I think I'll just sit here and push on the dashboard. You push. Does the momentum of the car change? So you push harder on the dashboard. What are you doing? You're pushing on the dashboard pushing back on you. What's the net force acting on the car? 0. So what's the change of momentum of the car? 0. See, that's why you got to get outside. You get outside, now you push. You push on the ground push on you. You push against the car, there's a force pushing on the car changes its momentum. You got to have an outside force. In the absence of an outside force, what's the change in the momentum of any system? 0. No change. It will simply transfer from one to another. I can show you that with another case of a collision. This time, I'm going to have my colliding cars are going to stick to one another. Okay? And so let's see what we got now. I'm going to move this car with momentum. It's going to hit here. Let's suppose 10 units of momentum. 10. It's twice as massive. One more time. From what you know about physics, I moved body A in with 10 units of momentum. That means its mass times its speed multiplied together to be 10. 10 units, 10 whatever, okay? It hit. Boom. Afterwards, you saw both of them moving. How much momentum for both? 5. Some people say 5. Where'd the other 5 momentum go? Let me say this, gang. Here's your system right here. When these things hit, was there an outside force acting on the system? Was there? No. So is there a change in the momentum of the system? No. So if this got 10 and this got 0, add them together, what do you got? 10. After collision, what do you got? 10. You got the same momentum before and after. Now here's the question you were asking back there. The speed. If the momentum is 10 before and after. Okay. What's the speed?
We can assume that they have the same mass?
In this case, they have the same mass. You've got one car coming in with a speed. Let's suppose the mass is 1 kilogram. So it's coming in at 10 meters per second. Let's just make that up. Okay? And it has a mass of 1 kilogram. So what's the momentum of the object? It's 1 times 10 is 10. 10 units of momentum. Okay? Now it hits another car. But this time, instead of bouncing, both cars move together. What's the momentum before and after collision? SS. Same. So what's the momentum after collision? But now I'm going to ask, what's the speed after collision? See why some people get mixed up? They get speed, momentum, mass. Oh, there's all these ideas. I can't handle them. I'm going to drop the course. No. Get some tutoring. Okay? You see the different ideas. So if you have twice as much mass moving with the same momentum, they must be moving with how much speed? Oh, not 10. Because now this is 1. This is 1. I got. Look at this. To begin with, the momentum before is going to be equal to after. Before, I've got mass of 1 times 10 mv plus, if this was a 0 at the beginning, remember it was 0? Boom, they hit. And then after they hit, I've got how much mass moving? 2. Both cars are moving. So 2 times, and here's what I got to figure out. 1 times 10 is 10. Equals 2 times. There are people what can calculate what this must be. Is there anyone in here who can't? Stand up. I want to see what you look like. What's this number here, gang? 5. And so we see, yeah, the 2 cars do move at half the speed. So they'll have the same momentum. I used to live out in Colorado, and I lived near a place where the railroad cars would get together. And it'd have like a lot of mining out there. It'd have sometimes like 80 freight cars going to be pulled to Gunnison, or maybe pulled to Pueblo or somewhere like that. And boy, it used to be tough at nighttime, because at nighttime these cars would all clank together, like the freight car would come up and they want to get them all clanked together. And it turns out that the coupling between the cars was loose. So instead of them coming up and boom, one great big clank, there'd be clank and then clank, 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 78, 79, 80. Okay, pull 80 clanks. And whew, now I can go to sleep. But then what happened is they just connected together. Now they're going to pull this way. And what happens is clank, 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 78, 79, 80. And I used to think to myself, why don't they take those couplings and tighten them up so they don't all clank? Why did they do that? Ooh. I know why. It begins with F. Physics. Hey, all right. It's because of the physics. Let me ask you guys a question. You want to set into motion 80 freight cars? 80? Let's suppose you tie them all together so there's no loose coupling. So when you start to pull, you pull all 80 at once. Fat chance. You know what's going to happen with that locomotive? Those wheels are going to spin. You ain't going to pull 80 cars. No way. You can't get that much force on your track. You can't do it. But you can do this. You can pull 1. And once you got 1 going, then you can pull another one. And now you got 2 going. Now you can pull another one, and then another, and another. And you can get all those 80 cars moving. By pulling them how? Stretch out the what? Begin with T, end with I'm. By stretching out the time, you'll have enough force of friction between that big wheel and that track to get all those cars in motion. That's right. Ain't that neat? It's like taking your courses in school. Do you ever take 80 units at once? Honey, you can't pull 80 units at once, right? It's like taking a summer course and maybe like 3 calculus courses in the chemistry lab in 10 weeks. You can't do that. You need more time. You like to see something neat? It's called a swinging wonder. Watch this, gang. I'm going to be lifting one of these balls up. That's strange. Only 1 ball came out the other side. I'm going to be lifting 2 balls up. That's strange. 2 came out the other side. I'm going to be lifting 4 balls up. No, I lifted 3, I said 4. I thought maybe it might be what I'm saying, okay? And it turns out it wasn't what I was saying. let's see what happens if I do lift 4 balls up. But there's only 1, 2, 3, 4, 5, 6, 7. Let's try it. That would be wild if 4 balls came out the other side now. If that were the case, it would seem that there must be some underlying rules applied here, huh? Let's try 4. And we got 4. Let's try 5. Wow! Let's try 6. Woo! Let's try 7. Okay. Yeah, ain't that neat? I wonder if there's a reason for that. I wonder if there's a reason. Let me ask you a question. When one comes in, whoom, it's got a certain momentum, right? That momentum transfers, and what comes out of you? How much momentum? The same or more? I say, oh, well, probably more. Come on, free lunch? No way, okay? When one comes in, boom, you get 1 out. 2 in, 2 out. Now, let me ask you a question. How do the balls know? You wonder about things like that, isn't that right? See? The momentum on one side, the momentum on the other side, the same. We say the momentum is conserved. It's just transferred through the system with none being lost and none being gained. So 1, 1, 2, 2, and like that. But I'll tell you what, gang. How would it be if I had 2 of these come down? 2. And 1 come out with twice the speed. If that happened, would the momentum before and after be the same? Think. 2 balls, certain speed. 1 ball pop out with twice the speed. Check the numbers. Can you do that? And when you do that, you find out that there's nothing wrong. But you know what? You could do this for eons and eons, and you never lift up 2 and see 1 come out with twice the speed. No can happen. Why no can happen? Because there's something else that has to be conserved besides momentum. And that something else is what we're going to be talking about next time. Begins with the E, gang. What's it going to be? Energy next time. Yay.